Duhamel's equation is this equation in yellow here, and in this video we're going to show how to derive that as the solution to this problem in blue. So this problem in blue is the inhomogeneous one-dimensional wave equation with homogeneous boundary conditions. So it's an inhomogeneous wave equation because we've got this function on the right hand side, h of x and t, and we have homogeneous boundary conditions because both the initial displacement profile of the string and the initial velocity of the string are both 0. So this is a problem that has solution given by Duhamel's equation down here. So how do we derive that equation? Okay, so here's an outline of the derivation of Duhamel's formula. So problem 1 here is the problem that we actually want to solve. It's the inhomogeneous wave equation with homogeneous initial conditions. But in doing so, it's going to be useful to look at a second problem, problem 2, which is a problem where we want to find a function w, which we'll say has got 3 arguments. So we'll say that w depends on x, t, and some value tau. And this problem is subtly different to problem 1, because if we look at it, well, first of all, the wave equation is homogeneous. It was inhomogeneous for problem 1, it's homogeneous for problem 2. And this is going to be defined not for t greater than 0, but for t greater than some parameter tau, which is this, this number that's going to be the third argument of the function w. Now when t is equal to tau, we have something that's a bit like an initial condition saying that at this time tau, then w is 0. And we also have an initial condition that says that the time derivative of w at that time tau is equal to h of x and tau, where h is this function that we had up here in the formulation of the original problem. Our approach to solve this problem will be to show that if w is a solution of problem 2, then if we integrate that solution w with respect to tau between 0 and t, and call that function u, then we're going to show that u is the solution to problem 1. Okay, so then, having shown that, our strategy will be to solve problem 2 via a change of variables and D'Alembert's equation. So once we've found what w is, all we'll have to do is integrate it with respect to tau, and that will give us the solution to problem 1. So that's the outline. It's really a kind of 2-step proof. Okay, so let's jump straight into that first step in the process, and that's going to be to prove this theorem here. But in order to do so, we're going to need this lemma, and the lemma says that if we have a function f that takes r2 to r, that's smooth, a smooth function of t and tau, and we define an integral like this to be the function uppercase f of t, then f prime of t is given by this expression here. So that will be a useful result to use in our proof. Then the theorem that we're trying to prove says if we let w be a solution to problem 2, which is the problem 2 that we saw a moment ago, then if we define u to be the integral from 0 to t of w x t tau d tau, for x anywhere in the real numbers t greater than or equal to 0, then that integral that we're calling u is a solution to problem 1. So that's what the theorem that we're trying to prove. So how do we prove that? The proof begins by using that lemma straight away, really. So if we let w be a solution to this problem 2, and then we consider u defined by this integral, then if we use the lemma, then the lemma tells us that the t derivative of u is going to be equal to w of x t t plus the integral from 0 to t of w t x t tau d tau. Okay, so if we look at this first term here, that's when the second and the third parameter are equal, both equal to the same argument t, and our initial condition for the problem w, in particular this one here, is telling us that this must be equal to 0. So this term disappears. So we're just left with the integral from 0 to t of wt xt tau d tau, and that is u subscript t, the partial derivative of u with respect to t. Okay, then we can apply the lemma again. So if we want to get the second derivative of u with respect to t, we hit this expression with the lemma, because this is another integral of a similar form. And the lemma tells us that that will be wt evaluated at xtt plus the integral from 0 to t of the second derivative of w with respect to t, xt tau d tau. Now again we can look at the initial conditions, and we'll see from this last condition here that this first term, wt, when the second and third arguments are equal to each other, gives us h of x and then whatever that second and third argument was. So in this case, the second and third arguments were both t's, so this is going to be h of xt. So that term simplifies. This next term stays exactly the same as the integral from 0 to t of wtt xt tau d tau. Okay, so let's collect what we've got so far all together. So we've got our two problems, problems 1 and 2. We've got an expression for u sub t and u sub tt, the second derivative of u with respect to t. So what next? Well, also in our wave equation we've got c squared uxx, so it would be useful to say what that is. So let's do that. C squared uxx is going to be equal to the integral from 0 to t of c squared wxx d tau. And because we know that w is a solution to problem 2, remember that problem 2 was the homogeneous wave equation, so we can rearrange this, bring the c squared wxx over to the other side, and we see that c squared wxx must be equal to wtt. So we can write c squared uxx as the integral from 0 to t of wtt xt tau d tau. So what can we say about utt minus c squared uxx? Well, if we look at our expression for utt, we've got h of x and t plus this integral of wtt d tau. And then if we subtract c squared uxx, that's subtracting this expression up here. And so if we do that, that expression is just the integral of wtt. So utt minus c squared uxx will give us hx of t plus this integral minus this integral. So those integrals are going to cancel, and we're just going to get that utt minus c squared uxx is equal to this function h. What about the initial conditions? Well, if we look at u of x and 0, well, because of how we defined u as that integral from 0 to t, if t is equal to 0, then that's going to be an integral from 0 up to 0, and that's just going to be 0. Similarly, u subscript t, that's the partial derivative of u with respect to t. When t is equal to 0, we can see from this expression over here that if we put t equals 0 into there, then again we've got the integral from 0 up to 0, so this will become a 0 up here. And the integral from 0 to 0 is just going to be 0. So in other words, that completes the proof of this part of the problem, because we've shown that u defined in terms of w is going to be the solution to the inhomogeneous wave equation, and these initial conditions are satisfied. So the way that we defined u, starting from the solution of w, gives us the solution to problem 1. Okay, so that theorem that we've just proved, that says that if we can find a solution to problem 2, then we just integrate it with respect to tau, and we get the solution to problem 1, which is the inhomogeneous wave equation that we're trying to find the solution of. So the next step is going to be, how do we solve problem 2? Because once we can do that, all we need to do is integrate whatever we get, and we'll have finished the problem. So here is problem 2. It's the homogeneous wave equation, because we've got 0 on the right hand side here. We've got things that look like initial conditions, but instead of being for t equals 0, they're defined when t is equal to this parameter tau. So the second and the third arguments are equal here. So this is similar to the kinds of problems that we solved using D'Alembert's equation, but not quite exactly the same. We can make it look more familiar by saying, okay, let's fix tau greater than 0. So tau is just some number greater than 0. And then define s as a new variable that is t minus tau. Okay, in other words, t is equal to s plus tau. And then if we define a new function uppercase u, which is going to be a function of x, s and tau, so this new kind of time shifted time coordinate s, as being w of x, s plus tau, tau, then we can rewrite problem 2 in this form. So we have uss minus c squared uxx is equal to 0. So this looks very similar, except we've got u's instead of w's, we've got s's instead of t's. But the important thing is that because we've defined s to be t minus tau, whereas we had t greater than tau in the original problem, in problem 2, we've now got s greater than tau minus tau, and tau minus tau is 0, so we've got s greater than 0. And this is good because this is more like what D'Alembert's formula lets us deal with. Also, the initial conditions, well, before, if you look at problem 2, we didn't have initial conditions defined at time 0, we had them defined at time tau. But now that we've defined the shifted time parameter s as t minus tau, then if we subtract tau from this tau, then these conditions are defined for time equals 0. So we have that u x0 tau is equal to 0, and we have that the s derivative of u of x0 tau is equal to h of x and tau. Okay, so this is now in a form that looks a lot more useful for applying D'Alembert's formula too. So having said that, let's apply D'Alembert's formula. So D'Alembert's equation gives us this in this particular case, because normally we'd have that term like a half f of x plus ct plus f of x minus ct. Well, what we've been calling the function f is just 0 here from this initial condition, and so we don't have any of that. So we just have the plus 1 over 2c times the integral from x minus c s to x plus cs h of, let's say, y tau dy. Okay, so we're integrating over this dummy variable y. So we found what uppercase u is. Now we can just undo the transformation that defined u with this shift in coordinates, because we don't really want an answer in terms of s, we want it in terms of t. So w of x, t and tau is just going to be u of x, t minus tau, tau. So that's from this relationship of how we defined u in terms of w up here. And then everywhere that we saw s, we're going to replace with t minus tau in this expression. So we get 1 over 2c x minus t minus tau, x plus c t minus tau, and the integral between those values of h y tau dy. So that is now the expression for w. So we've solved problem 2, we know what w is. So finally, let's collect together everything that we've discovered so far. So we have that w is given by this expression here, and that's the solution to problem 2. So that's what we've just derived. And earlier we showed that this theorem is true. We proved this theorem, that if w is a solution of 2, and we've got one of those now, then if we define u as being the integral of that solution with respect to tau between 0 and t, then that will give us a solution to 1. So now we just need to combine those two things. In other words, we've got w, we just need to define this integral, and that will be the solution to 1. Okay, so here is the result. So all we've done to get this is integrated this expression in pink at the top with respect to tau between 0 and t. So we've got 1 over 2c times the integral from 0 to t d tau of this function here, what we call w. So the integral from x minus ct minus tau to x plus ct minus tau of h, y and tau dy. Okay, so that now completes the proof and we've derived Duhamel's equation.